hushed up. This is a well-trained group. You're all here. You're all in your places with bright, smiling faces. Before I start, I do want to thank you all for showing up. It makes such a difference to our speakers to have a full audience of smiling faces. It's good energy. Okay, in the back. Well, good evening and welcome to the United States Geological Survey's June public lecture. Before we get started, I always want to plug next month's lecture. We are having a lecture in July, on July 25th. It's going to be by Jake Wilson, and he's taking the pulse of our planet. It's the 10-year status report from the United States National Phenology Network. There's flyers in the back, and I encourage you to pick one up so you can save the date on your calendars. There's also there's some materials I think that Paul brought that are back there, and so hopefully you've had a chance to, I can see some of you have them, pick those up and look at those. But moving on to the main event, what you're really here for is tonight's lecture, which is USGS Fire Science, Understanding Why Wildlands Burn and What Can Be Done About It. And we're thrilled to have it presented by Paul Stebline. Paul is with our Ecosystems group from Reston, Virginia. Paul has nearly 30 years in government service. He began as a scientist with the New York State Biological Survey, then joined the Fish and Wildlife Service as a regional biologist and GIS coordinator. He set up a regional GIS data center for the service and prototyped numerous geospatial applications for the National Wildlife Refuge System. Then he went to the field, setting up biological programs at 3 national wildlife refuges in New Jersey. Next, Paul went to the refuge system headquarters, and he worked on strategic planning and then became chief of budget, overseeing its $600 million budget. Paul went back to the field to manage the nearly 1 million acre sagebrush steppe of the Sheldon and Hart Mountain National Wildlife Refuges, and they're located in the corner of California, Nevada, and Oregon. He addressed interesting challenges like feral horses and burros, cheatgrass and wildfire, and the Ruby Pipeline. Paul then went back to refuge headquarters to become chief of policy for refuges. And in 2014, Paul became deputy director at the Office of Wildland Fire in the Department of the Interior. He joined the United States Geological Survey, which we're really happy about, in 2016 for his current position as Wildland Fire Science Coordinator. That's a mouthful. Anyway, the USGS monthly public lecture series is pleased to bring you a program this evening about fire science. I'm going to ask that you all know this to please hold any questions till the end, but let's give Paul a really warm welcome.
Thank you, Diane.
Thank you, Paul.
I'm going to put in a plug for the seminar next month. Jake I know pretty well, and he's a good speaker, full of energy, and I'm sure you'll have a good time learning about the phenological network. So I come at this different than the traditional scientist. I've spent most of my career as in management, and it's a pleasure to be here with you tonight and hopefully address some of the important topics associated with wildland fire. And certainly it's a privilege to be with USGS. But I come at it from both the science and a manager perspective. What is the science we need? What information do we need to make the hard decisions on complicated issues? And so even though I was in management for quite a long time, I was always an ardent and passionate user of the results of USGS and others in the science community. And so I'm not an expert scientist in any one of these subjects, but I know a little bit about a wide variety, and I want to make sure I'm giving credit to the more than 100 scientists that do produce all this wonderful information that we need to use. And so I'm going to be highlighting some of this, the research and the science, as we walk through and try and address some of these questions. How many of you either have been affected by the fires or know people that have? Raise your hand, please. you're right in the center of all of what's taken place. California is the front line. And even if you don't know someone's house that may have been burned out, you are breathing the smoke through the summer when the fires in Alberta or through the West are affecting us. So it's important to know why fire is important, and you are vested in it already. We also need to know what is causing this, and you probably have heard quite a bit about it, whether in the news or maybe you're reading some of the science about it, and what is being done about the fires and how to address this. And I can highlight what's next, but I want to make sure I save time at the end to address questions that you have. By the way, this is the Lake Christina fire in Cobalt, Colorado. I took the picture last summer while at my niece's wedding, and she was frustrated because I was always on checking out the fire, taking the pictures. Cool, look at this, but it's 2 miles from where the wedding reception was, so she thought I was just a crazy uncle. But the day before, this was just smoldering, a little bit of smoke, and then the winds kicked up, it was hot and dry, and it made a 7,000 acre run. And you can see the angles of the clouds here. This is actually a vortex rising up because generated by the heat of the fire. So why is it important? Well, one is, this is from just 2018 statistics, but almost $5 billion was spent just on suppression. And that's federal and state fire suppression, which is a massive amount of money. But the National Institute of Standards and Technology did a review in 2017, in the last bullet, highlighted that they estimate, based on the review, between $72 to $250 billion a year is being affected by wildland fire. And now there's a lot of good stuff, but there's also a lot of bad stuff too. Last year, 8.7 million acres burned as compared to the 20-year average of 6.9 million acres, and I have a graph to show that. 25,000 plus structures burned, many of those homes, and many of those in California. There were $11.4 billion of claimed losses in California. There were 120 fatalities, including 19 firefighters. That doesn't include all the other health impacts and other factors associated with people. Now, on the good side, 6.4 million acres were burned with prescribed fire or planned ignitions to help achieve resource benefits as well as reduce future fire risk. And so we'll be looking at some of this information. This is just the suppression cost showing the increase over the years. The red line horizontal is the 10-year average of $1.7 billion, and that's how much it cost last year. This year is a little bit different in terms of the total acreage. It's a little bit below the year-to-date average, but you never know what's going to happen as the fire season continues on, which, by the way, they're defining as a fire year now rather than a fire season, because there's always fires burning someplace. So one of the big patterns that is evident is that the fires are getting bigger, more intense, and the frequency or the number of large wildfires is increasing. This is merely just a graph showing the total number of acres a year. That's 6.5 or 6.6 million that I mentioned earlier. That's this arrow here shows where that level is, but that's just the total acreage. So they're getting bigger and badder, if you will. But one of the important things, so let's start addressing the questions, what's going on? Well, one of the important things is the vegetation in the United States and actually around the world usually evolve with some kind of fire as a part of the ecosystem, as a driver for it. And this is a map produced by one of our programs, the Land Fire Program, that shows the fire regimes patterns that are across the country. And so the fire is an important part. It's an important driver in many of these ecosystems. They're adapted to fire or actually may need fire for seeds to sprout or cones to open up and drop seeds. It's an important component of it. And just for an example of some of the range, let me see if I can get the arrow up here. There it is. Okay, so down the southeast, pretty frequent fire interval down there. And I'll have a picture later on that shows that actually in a number of the stands, you need fire every 1 to 3 years. Now out west, out in the Sierras here, where you have the ponderosa pine, my mouse is jumping around, out here, it's more of, say, 5 to 30 years is a common interval to have a healthy, functioning ponderosa pine forest. And so one of the factors that up here is accumulation of fuel. So one of the problems that has taken place is for 100 years, there's been aggressive suppression of fires. So it's a much reduced area of land that has burned and frequency of fires that have burned, and so you accumulate the fuel. The common fire portrayal is that to understand fire behavior, you need to know about the fuels or the vegetation, the terrain, and then the weather factors. And so a lot of it is based on that. But fuel is the part that we have the greatest control over. And one of the factors, and I'm going to be hitting on a few of these, illustrating with some of the science that we have, change in climate and more extreme weather patterns. Development in the wildlands, so the building out of the houses, the roads, or the other infrastructure. Effects of invasive plant species and insect disease outbreaks, accumulation of fuel that I've mentioned, which has resulted in high cost and complexity of fighting fires, which also makes it more difficult then to manage the fuels, to do what we can to reduce the fire risk. So we'll touch on this. And I'm trying to sprinkle all through here the scientists. They're the people that are doing the work. I just talk. But Craig Allen and Ellis Margolis are a couple people that have done a lot with looking at fire history and regime patterns. So one of these is change in climate and weather patterns. So we're seeing an increase in warming temperatures, and that varies across the country. We're seeing increased periods of drought and more erratic precipitation. So when I say erratic precipitation, we may have a lot of snow, a lot of moisture one year, which then you see a flush of growth of the grass and perennials and other plants, which creates the fine fuels. And when it cures, like it does on an annual basis, or if there's a drought, that fine fuels becomes the ignition point, whether by human or by lightning or some other cause. This results in increased intensity and size of the fires because it can spread easier, it can get broader, longer fire seasons. Some of the length in fire seasons, John Keeley, one of our scientists who's done a lot of work in California, has pointed out that it's part of the reason for the longer fire seasons is we have people out there starting fires, whether accidentally or on purpose. So where you might not normally get a fire start, you may because of people. And then, which also affects the direct and indirect effects of the fires. So this is a study done by Sankey, published in 2017. And up here where you see the redder areas, that's where you see a major forecast for the next 50 years where you expect to see a lot more fire, which then has indirect effects of increasing sedimentation, erosion and sedimentation due to the fire. So climate is causing some changes in patterns, which then has an effect upon erosion and sedimentation rates. And by the way, I have a display copy, but the postcards that were out have a link where if you want to, there are over 900 studies that are compiled from 12 years' work of scientists, and most of them have links that go right to the paper. So you don't have to trust my word. You can go right to the paper and read and look at the science that we've produced. Another factor is development in the wildlands. And so this makes it building out the houses, the cabin in the woods, the running the power lines or pipelines or the other infrastructure. People need to do what they need to do, but the result is it makes it more expensive and complicated for fire management. You have to be, if you're a fire manager, you have to take extra precautions if you're doing a prescribed fire or doing other work. There's a greater chance, wherever you have people and fuel, there's a greater chance that you'll have ignitions. And so that's a big concern. So if there's a road or a pipeline, whether it's, again, accidental, someone parked a car with hot metal pipes over grass that can start, which is very easy to do, or I think one of the fires was started by sparks resulting from a flat tire, so from the rim, the metal rim hitting the road. So there's a greater chance of these ignitions. And there's also a greater chance of invasive species. So when I was at Sheldon and Hart Mountain, along the roads, and primarily only on the roads and 2 tracks, is where we found cheatgrass, Russian thistle, halogeton, all these other weeds that are a problem for fire as well as for biological integrity of these areas. This is a study that was Todd Hallbreaker was one of the scientists, and so they looked at the change in WUI from over a span of 10 years, and it's hard to see on this, but where you see the red, and there's going to be a lot of small red pixels sprinkled all through there, but that's where they've seen the biggest change in build out into the WUIs. And so that's what scares, I would say, fire and land managers more than anything else, because there is so much buildable land out there, and the result is it is getting built. And so again, it changes the pattern. Invasive species I mentioned, and so these are a couple of the bad boys across the country. So the colored polygons there indicate where some of these arid lands are, the arid shrublands. So the reddish here is the Great Basin. We have the Mojave and Chihuahuan deserts, and I'm not familiar with, actually it shows it there. So Chihuahuan, Mojave, Sonoran, and Colorado Plateau. And so cheatgrass is probably has the worst reputation, and well-deserved, for really flipping upside down these fire regimes. And so the high bush, high sagebrush, and then the low sagebrush, these are areas that burned 50 to 200 years. And low sage, maybe more than 300 or 500 years was the normal fire interval. But when that cheatgrass, have you ever seen low sage? I mean, it looks like an alpine environment. You don't think a fire would carry there, but when you put some cheatgrass in and a wind, it'll plow right through. So it's flipped it right upside down. Red brome is another. These are fire-adapted weeds that come in, and the next slide shows a little bit more about how that takes place. Buffalo grass down along the border. Mediterranean grass. And so on one hand, these are fire-adapted weeds, and so it has changed these fire regimes. But for many other invasives, fire is actually a very good control measure, and I think I had a report out there that actually was a compilation of how you can use fire to control other invasive plants. So anyways, Betancourt did this really nice compilation of work. Seth Munson, actually at one of our community of practice calls, used this graphic to illustrate the issues. There it is, the right one. So the sage steppe and the southwest deserts, this is especially apparent. So the normal vegetation distribution, there's openings. There's a lot of openings in between the shrubs and the trees. This, I think, is a Joshua tree, so indicative of Mojave Desert. But there very rarely do fire ignitions take place there. And then you have the incursion of a fire-adapted weed that actually gives you a more carpet of fine fuels that when the lightning strike hits, and a lot of these are remote areas, when lightning strikes, you can catch and spread, which kills the shrubs, or native shrubs and trees. And so the response after that is usually the fire-adapted weeds come back quicker and can, in fact, partially exclude the native plant restoration. And so then that burns more frequently, and that cycle is just increases the amount of cover until you have these monocultures of cheatgrass or red brome or buffalo grass, and it's devastating to see that change take place over hundreds of thousands of acres. So this is an area of work that a lot of our scientists work on because there's no silver bullet. There's no easy control that's been found for a number of these. And so they're working with a lot of different techniques. So what's being done about fire? You all are impacted in some way. What has been done, or what can be done? The logo up there is for the National Cohesive Wildland Fire Management Strategy. Back around 2009, I think, Congress said, hey, you got to come up with an integrated strategy, a cohesive strategy to deal with this. And so federal fire and land managers worked with state foresters and fire managers, worked with local communities like NACO, the National Association of County Organizations, many NGOs, and they put together an impressive set of reports that culminated in the strategy itself that was signed off by the Secretaries of Interior and Agriculture in 2014 that says, hey, we need to do, it's all hands, all lands. Everybody's got to work together on this because fire doesn't recognize boundaries. And they have three main goals. We need to restore the resiliency of the landscapes to fire. In other words, to have it more resistant and recover better after a fire takes place. So that gets at fuels management, things like that. We need to have fire-adapted communities. And so people need to take responsibility and create defendable space, look at how to harden their homes to make it more resistant to the impacts of fire. And then third, we need to respond to fires in an appropriate way. In some cases, that's put it out. In other cases, try and use wildfires to reduce fire risk in the future by removing or reducing some of that fuel. So then another important step, recognizing that we need to actively take care and do these things, was the Executive Order 13855, which was signed December 21st, and then followed by the DOI secretarial order to implement that. And it reinforces some of the key principles of the cohesive strategy, protecting people and communities, promoting healthy and resilient forest, rangeland, and other federal lands, and working together to actively manage and reduce this fire risk. There's a lot more in these, and I would encourage you, if you want, take a look at it, but there's a lot of good stuff in there. And it's galvanizing people to work together to address the issue. No one person, no one group can do it. So when I started with USGS a couple years ago, I was first of all surprised by, you do fire science in USGS, and actually there's well over 100. I've got a community of practice of scientists that I work with that there's 150 subscribers now. And it was breathtaking to see the variety of work that's being done and how many are doing it. It goes from everything from the Eros Science Center in Sioux Falls, working with land fire data, which you've seen a couple of images of, to working on what happens with debris flow afterwards. Anyways, I tried to find a way to understand, capture it, and illustrate it simply, and this is a story map to try and do it. There's a much more complicated picture at the end because it really does, to integrate all this, does get kind of complicated. But it represents a variety of management, a variety of disciplines and themes, and what I'll try and do is organize it under these four to convey a little bit simpler this whole picture. So fire management, fire ecology, post-fire effects, and geospatial. So fire history and management. A lot of people have heard about certainly Smoky Bear and Forest Service research and development. They are a go-to place for fire science, but it emphasizes the forested environment. USGS and Department of Interior, many of the lands are actually non-forested. It's desert, shrublands, grasslands, wetlands, tundra, and then forest on DOI land. So this map illustrates the distribution of the 500 million plus acres that the Department of Interior is responsible for, and USGS is a prime science agency to understand and address those challenges on those lands. So a lot of what's being done is understand the current and historical fire regimes, which we saw a map on earlier, explore and evaluate the effectiveness of these fuel treatments. When you're spending hundreds of millions of dollars a year on fuels treatment, you want to know it's going to make a difference. It's not being thrown away. Bear team support, so burn area emergency response teams. This is a specialized group that comes in after a fire to assess what's the state of the landscape out here after there's fire, are the things we need to do to stabilize it right now so that it doesn't get worse. So supporting them with imagery, scientific information, how to recover it. The effect of invasive species, which we heard a little bit about already, ignition sources, climate change. How are these affecting fire risk? Factors that affect housing losses from large fires. And then what vulnerability in ecosystem services that are at risk. Understanding the bigger picture and how we can ameliorate some of those risks with fuel treatment planning and other things that communities can do to help reduce those risks. So fuels management, that, and again, in the fire triangle where we have terrain, fuels, and weather, it's really the fuels that we can, which means really the vegetation, that managers can go out and reduce risks with that. And so big part of it is focused on efficacy of the treatments, reduce the risk, and then what is the effect of those treatments? So there's hard trade-offs usually. What are the effects that fuel treatments have on the plants, animals, and ecosystems that these DOI land managers are charged to protect and manage? And so a lot of those active management treatments include things like prescribed fire, building fire breaks, forest thinning, and invasive species control. So this is a two-track, or some called Jeep Trail, out in the high desert of the Great Basin. And Doug Shinneman and some of his colleagues did a review of what is known, this was over about a year ago, what is known about these fuel breaks and the ability to stop fires. And so they found some very interesting things. One is that there's not a lot of published, peer-reviewed, objective studies that were done. A lot of it is anecdotal or published in great literature. So that was a gap in the knowledge base that's out there. The other is that it's not just the disruption of fuel to stop the fire in itself, because a rip and fire can jump that pretty easily. It's the ability to safely put a fire crew out there to be able to either backburn or do other things to reduce the impact without putting their lives in jeopardy. And so that review that they did spawned then a couple of new studies where we're looking at using fire models. We're looking at some new fuel breaks that are going in to try and keep the fire smaller in the Great Basin. But they're setting up experiments to really expand the knowledge and knowing what works and when doesn't it work. At what temperature and when will a fire jump this? And the only thing you have to do is get the crews out of the way, because you're not going to stop it. Very interesting going to some of the fire meetings over the last month that in California, for instance, one of the results of the last 2 years is, especially with Paradise, it's need to do fuel breaks along the major evacuation routes to assure that people have a chance to get out of there. When you have a wind-driven fire, and we'll talk a little bit about wind-driven fires, when you have wind-driven fire, you have hours to take your action, and that's it. And so, a lot of people are looking at how to keep you all safe. The one picture in the upper right corner is a loblolly pine stand, and there's some longleaf in there as well, down in northern Florida, Osceola National Forest. And just to illustrate this is 1 year after a fire. Look at that thick layer. That's about 3 feet tall. And this is 3 to 5 years after a fire. And so vegetation grows incredibly fast. It's a lot of it's fire adapted. It has volatile oils in it, like saw palmetto. And they have to burn. There's a culture down there of doing a lot of prescribed burning to keep the natural regime going. Otherwise, it's very difficult to control the fires there. So this map is fire regime condition class. So if you think about the fire regime we saw before, what parts of the country or what areas are out of compliance with that time interval, that natural fire regime? And so the red colors indicate where, the red colors indicate areas that are out of compliance, and the black circles indicate where we have scientists doing work on this. So again, this is a land fire derived data, and I'll talk about that more later. So a key part of this, the goal was fire-adapted communities. John Keeley, who's done a lot of work in California for many years, set up this study with a couple colleagues and looking at what are the factors associated with loss or impact to communities. So they collected fire damage data using aerial imagery. If you look very carefully, there's a house here before a fire, and there's not a house here after a fire. So assessing where were the impacts, identifying what the landscape factors that contributed to those fire risks, and what are the home factors. Home factors being, what was the building made of? Was there fallen debris on the roof of the home? What factors like that affected it? And then evaluate the efficacy or how effective the vegetation, the defendable space concept worked to protect the house. And one of the things that they found out is, it's very important, if you have leaves in your gutter or a tree over the house and there's a collection of branches and fuel on top of your house, especially in these wind-driven fires, the embers that are driving out can have a big impact on what homes are burned and which are not. And so they're continuing this work because some of these fires in both Southern and Northern California and many other places as well, there's an interesting contrast coming out between wind and fuel-driven fire. John just published a paper on that, and it really points out the importance with wind-driven fires to do the work ahead of time. You don't have time to run your models and do all the evaluations. You really need to know ahead of time where the safety zones are, where the evacuation routes are, and what are the patterns of fire that are likely to take place. And this has been a discussion in meetings that I've had with FEMA and Fire Administration, the Wildland Fire Leadership Council. A lot of people are, in California, I would say, I'm very impressive that they are doing a lot quickly to try and address the problem. So I know there's big challenges ahead, but there's also very good people working on it. So one of the other kinds of information is, how do you support the firefighters that are responding? And one of the areas that we provide support with in conjunction with the Forest Service from our National Civil Applications Center is, where are the fires when they light up? How do we get that best information, know where fires start? How do they spread? So what is the change in the perimeter that takes place? And the most recent information with some of the satellites and capabilities are, where are the hot spots on that fire? Can we map that out? Can we move it towards real time? A lot of discussion is taking place right now on how do we move it to almost real time to know what's going on with the fires when they're out there. And so this is the Noisy Creek fire. And if I can get the cursor here, this shows a 24-hour perimeter, this red line. And then these are hot spots. So these are where there's actual fires sufficient to be detected to show where the active head is. So this is coming up to the water here. Hopefully there's other information that can say the likelihood of it spreading across that big body of water, but it certainly says this is the head of a fire in a front that's moving out. So trying to provide that as quick and as dependably as possible is an important support that's needed by our firefighters. So wildland fire ecology and restoration is another big area of work. So what effect does wildfire and the fuel treatments have on our species, habitat, populations, and communities? And this is across a broad set of taxa and ecosystem type activities. So plants, fish, invertebrates, reptiles. This is a couple of these species are down in Southern California. Robert Fisher is working on that with the salamander, and that may be a a thrasher. I'm not. California thrasher. Great. The sage grouse, though, there's been a tremendous invested in understanding the change in population and conservation of sage grouse and how it relates to fire. And I'll talk a little bit more about that. How do we use prescribed fire as a surrogate for wildfire? We talked about fire-adapted species, native ones. How do we use it to get those benefits for those ecosystems and do it safely? And then post-fire recovery and restoration. So how do the plants and animals respond to that fire, and how do we lessen that impact? How do we better control invasive species, and different ways we can foster recovery and restoration of desirable vegetation afterwards. Also looking at the complex interaction between these invasive species, resource management, and when I say resource management, so what kinds of land uses out there? Is there grazing? Is there timber? Is there recreational things that may make it more difficult? And of course with wildfire. What climate change and other factors that affect vegetation, fire behavior, and the carbon dynamics. And then the last one is more for up in Alaska, but what's going on with wildfire vegetation, biogeochemistry, and permafrost? Alaska is a very different beast, and anyone from Alaska says that. But natural cause fires were very unusual in Alaska until the last few decades. With increasing temperature, they started getting these storm systems, the cumulonimbus and lightnings, which they never really saw in lightning much before, but there's now natural fire starts, and actually fires in the tundra even. And so we've got quite a few people that are working with University of Alaska to look at that. So this is post-wildfire restoration. Again, invasive species are a real challenge. This is a sagebrush steppe, and with sagebrush, a good intact system shown here before and what it looks like after a fire. Looking at this is how do we foster the resprouting of sagebrush and the native species, and doing very interesting things like with looking at what's the role of biological soil crust in these arid areas to foster the regrowth of the native species. One of the really very neat, when I was in Office of Wildland and Fire before, back in 2015-16, they had this big workshop, bringing all the scientists and managers and anybody with a really big stake in it together to say, what's going on in the sagebrush, in the sage steppe? What's going on with the sage grouse? How is fire tied into it? What do we know about it? What are the best practices can we bring to bear? And what don't we know that we need to figure out? And so that last part was captured in this integrated rangeland fire management strategy actionable science plan. That's not easy to say without stumbling. But it was exciting to participate that and to see that. And that is the blueprint for the research that's been taking place that we have funded, that I've funded with my small amount of funding. The Joint Fire Science program has put several $1 million towards, and certainly Bureau of Land Management and other agencies have invested as well. And again, there aren't silver bullets, but they're evolving the techniques to better understand how do you combine herbicide treatments or reseeding, how do you ensure the success of that as much as you can, and reduce the unpredictableness and be more efficient with the investment of funds. So a lot of research has been expended on that. And let me just point out sage steppe. When I was at Sheldon Hart, on Hart Mountain, we hosted two of the experimental plots that there's 14 of them, I believe, across the whole Great Basin. And it was just phenomenal to see a great scientific design applied to understand these interrelationships. What are the social economic aspects of it? What are the impacts of these different treatments? How do we move it forward? And then the continued interaction with the managers from the scientists. And it's a broad group of scientists from Forest Service, USGS, universities, and other agencies. So that was one of the first real co-production efforts that I saw. And then this was, the Actionable Science Plan was the next step that I think helped evolve it. And then this 2015 soda fire, this is a 250,000 acre fire up in southwestern Idaho. Matt Germino, one of our scientists, worked with Bureau of Land Management. They invested a lot of money into trying to restore it and recover it after that fire. And so they set up these experimental treatments as well as just the regular treatments, thousands of monitoring plots to understand as best possible how different factors affect it and how can that be layered together to ensure the greatest success. So very interesting results coming out of that. One of the other big areas is post-fire risk assessment and management. Fire has effects. And so we have quite a few people looking at how it changes, how elements in the storm flow, the ash, the burned soil, how that affects both humans and ecosystems. So I know there's a lot of focus with air quality on ozone and in particulate matter, but there's a lot of other components that are dangerous and difficult to deal with. And so we have scientists looking at that. What's the difference between wildfire and structural smoke? So as these fires start rolling into the WUI, the wildland-urban interface, is that the same or different, the component parts that come out of that? And it's in one of the take-home messages is there's some pretty noxious stuff coming out of the man-produced, human-produced structural elements and what you find in developed areas. Also looking at different kinds of hazard assessment warnings and reduction of the effects of flooding, sedimentation, and debris flow events. And so I have a couple of illustrations of that. Fire effects on water quality and quantity and water supply infrastructure. For California, the water infrastructure is really important. And I know is a big issue in terms of how to maintain it and deal with factors such as drought. And then one of the things that surprised me, and I didn't think about but sure makes sense, we have Matt Germino on the prior slide has actually been setting up studies to monitor what happens after a fire with wind erosion. And that he has found that on some of the sites lose 3 to 5 inches of the top layer of organic and particulates and material that then, if it's blown by the wind, creates some of the dust storms that you can see in these arid areas. So it affects air quality as well. So we've been talking about vegetation a lot, but vegetation has a key function here as well. So this is a fire that was in Fish Lake National Forest in Utah. And you can see that, I think this is within 1 year after the fire. A lot of stems left, but that's a lot of mineral soil shown there. And I've been to some places down at Jemez Mountains where it is just a total moonscape. There's no visible organic matter left at all. It's just rocks and mineral soil, gravel. So one of the things that we do is characterize the burn severity. So that is, to what extent is the original vegetation organic matter still there and able to function to absorb water or provide cover to stop wind erosion. And this is a map up here showing it with 4 categories from extreme to low effect. And that's used by, you'll see in the next 2 slides how that's used. This also captures some of the historic information on fire. So this is the Monitoring Trends and Burn Severity, MTBS, viewer that you can look at. And look from 1984 to 2016, they have it captured. And so you can look for fires over 1,000 acres, what's the distribution of burn severity across those fires? And what is the fire history for 1,000 acre plus fires across the country? So this is one of the key data layers looking at debris flow risk and warning systems. So one of our programs, and they do dozens and dozens of these each year, many of the fires in California, what's the likelihood of debris flow or a landslide type event, potential volume of that debris flow, and the hazard to human infrastructure, to people. The model uses information on size and shape of the watershed, so the terrain, the burn severity, which we just talked about, so how much vegetation is there to help hold that matrix in place and impede the effect of water coming down. Soil properties, again, similar physical aspects that affect its vulnerability to debris flow. And rainfall characteristics, is there enough precipitation to cause a debris flow to take place? These maps are used by emergency managers for warning systems and BEAR teams, the Burn Area Emergency Response Teams. You know, what can be done for stabilizing or a quick response or other types of mitigation. There were, when I put this together a month ago, this slide, there were 56 mappings available online. That's the website there, and that's one of the maps that shows, again, various degrees or likelihood of a debris flow to take place. The upper right picture shows, is one of the landslides where a house is buried by it. And let me go to show you a live video from one of the monitoring. This is going to go pretty quickly. This is monitoring one of their sites. And I don't know if you can hear it or not, but those boulders on the upper right side, the one at the top is almost the size of a car, and the one in the center right is the size of a dinner table. And you're going to see boulders coming through. Look at that. That was almost a dry waterbed before the event, and this is all the upstream debris and rocks flowing down. Some of those rocks are the size of cars coming down. That was a tree that just went by. And that just reshapes the channels, the whole terrain when these events take place. And so, again, a key part of this is when you lose this organic matter. Oh, this is not good. Let's snooze. Okay, did you see that rock go by? Just massive impact that this can have. Thank you. There we go. Sorry about the transition here. Okay, so let's go back. So they are mapping this out at the request of local communities and fire and emergency management teams. Oh. That video really wants to run. That's another one. I could look at these all day. Again, trees going, no, that wasn't trees. You can see the shrub vegetation, sorry. I get excited about this. It is, this is big, dangerous stuff, but it is amazing the intricacies and how it's all interconnected, and I do love learning about it, and it's really important, the information that we are producing, or many people are producing. Another big impact is post-fire water quality and quantity, and so the fire changes the physical and chemical properties. This organic matter, the vegetation, it impedes the impact of raindrops. It helps shade snow. So there's some physical characteristics there. But it changes from a sponge, essentially, to absorb this moisture and foster infiltration to actually repelling it. And so I've done this. You go out after a fire, you put water on, and it balls up. It doesn't get absorbed into it. And so this is a study that Sheila Murphy, Brian Ebel, and several others, colleagues, did in 2018, looking at what are the differences. So this is a normal landscape here with trees and litter and duff that presents this matrix that stabilizes the soil and helps in the infiltration of water through the bedrock and soils downstream in a way that can recharge aquifers, but also does it at a manageable process. And this is shows the range of suspended particles or solids, dissolved, organic carbon, and then a variety of solutes in materials that are dissolved. And then this is nitrates, fertilizer, one of the components of fertilizer. And this is what's in a normal functioning ecosystem. Then after water, this is the different. Look at that contrast. And it's a significant difference in terms of what's eroded into suspended solids, what is represents carbon that's in the streams, and actually, if you look, that last video showed a lot of suspended stuff in that water, and some of it was not very small. The variety of solutes, the salts and different nutrients and nitrogen. And so the big difference is rather than infiltrating through, the path then becomes more of on the surface. The majority of the water runs sheet flow down into the streams and has many downstream effects too. So anyways, where we're at with a couple of these things, the debris flow, what they're working on now is can they map out the potential for an inundation. So where's all that material going to go? What infrastructure, what communities are at risk from that? That is what everybody's asking for. And I think we're going to be kicking off a project this year to try and develop a model for that, which is pretty challenging to do. The other part of it is, how do we map this before a fire takes place, rather than map these risks after a fire? How do we do it before, so that you can then prioritize the fuel treatments and other kinds of mitigation measures to reduce the risk of this? And so and another one is, how long does it last? When do you restore the normal ecosystem function, the stabilizing and vegetation layers on top? So the last area to talk about is remote sensing geospatial technologies. You've been seeing a few of these. This is an MTBS map, that burn severity map. Land cover, land treatment digital library. So this is all the different kinds of sensors, hyperspectral imagery versus multispectral, using UAVs, high performance computing, data access. How do you make this available to any of you to look at as well in easy to view interfaces? There's archives of aerial photography and digital maps, elevation products, all this kind of stuff. So one of the new technologies is LiDAR. There's other technologies, structure through motion, using stereo imagery, that you can reconstruct point clouds like the image on the left. LiDAR is light detection and ranging, uses a laser to measure the distance. But you have many thousands points of lasers going down to measure, do those vertical projections, to look at and characterize the vegetation, the fuels. And because fire behavior is dependent upon the nature of that fuel, the type, the quantity, the condition, how much moisture is in it. So how can we improve the fuel modeling? And we'll talk about that in a second. But fuels are highly variable over space and time and difficult to measure. And so going from just like an aerial photo or a Landsat image, we have a great deal more structural information we can develop from this. This is Birgit Peterson and Curtis Nelson up at Arrows. There's a couple of other scientists. Matt Brooks is working on this, and then a number of people from Forest Service R&D. How do other disturbances like bark beetles or drought affect it? And then actually there's so much that you can do with LiDAR. It's still very expensive to put commercial planes up to capture it, but they have sensors downsized enough to go on UAVs. We've got a project I'm starting up with some colleagues down on the southern border to characterize before and after fuels and treatments and fires. How do we characterize that? Land fire, this is meat and potatoes. Has been for quite a few years. It's maps and data on vegetation, wildland fuels. You've seen some of the images already. This is vegetation type, one of the vegetation types, as opposed to regimes and other things. Departure from historical condition, and also the terrain characteristics. This is all the information you need for fire behavior models. They're using this information for management planning, to produce the fire plans that all the land management agencies are required to produce for all the land that they're responsible for, to help in responding to fire when it takes place, and to prioritize fuel treatments that are out there. During fires, it's used for decision support and WFDIS, which is the Wildland Fire Decision Support System, where it's the data that drives the fire behavior models. Also points out key characteristics that are out there that they're trying to protect, sensitive areas, for instance. And then after fires, to help inform what was out there before, what is the desirable vegetation after fire, and help develop the bear plans. GeoMac is another application. So we have a few people that work with the fire management community at the National Interagency Fire Center to map out where are the fires occurring, what are the 24-hour perimeters, so that you can look at the change in spread of the fire. And actually, they've gone back in time to capture it as well, so you can look at historic fires and how that's important when you have a fire incident management team out there and looking at where the fire is going to go. If there was a recent fire and reduced fuels, then you understand better what the behavior is going to be. There's also a public viewer, so you can, this is, shows the different fire outlines over the years, so that's where I go to look at what's going on with this fire or the spread of fires across the country, to look at the change in fire activity. You all can access this. So what's next in fire science or with all this stuff? The map, I kind of like this one. This is it's a map of cheatgrass, and it's near real time. Near real time for that is within weeks of the cheatgrass senescing, drying out, curing, and where it becomes a fuel. So that we're doing that every year now to characterize with a seasonal change in fuels and fire behavior. That sage steppe project that I talked about, that's on Hart Mountain when we put the plots in place. So that's what sagebrush looks like when you light it up, and that's a Landsat schedule. So where are things going? Well, we have a community of practice, the 150 scientists. We have monthly calls. We try to coordinate and collaborate as much as we can. We're developing a strategic plan for fire science at USGS. It's not an established program. It is these scientists across the whole agency working on all these disciplines. There's a lot of discussion taking place about how do you integrate and collaborate fire science across all the federal agencies and with the universities and with the others. The Joint Fire Science Program helps do that, but there's a lot more that needs to be done and can be done. And so there's a lot of discussion taking place. There was the White House Subcommittee on Disaster Reduction in 2015 issued a report with a recommendation, strong recommendation for how to set up that kind of community of practice across federal agencies and with management. So where are we at with fire science? And I have two slides just to illustrate the concept a little bit. So there are models, to characterize what happens with a system when you do something. And so there's fuel models and consumption in the center here. And the current system is very simple. It's a couple dozen categories of fire fuel type that's used in these systems. It doesn't characterize it over the landscape in any kind of continuous or three-dimensional way that really you need to understand fire behavior. Fire behavior models are based upon 1972 study that was done that produced the raw thermal equation, and it's just a statistical pattern that's used to model the spread. It's not based upon real fire behavior. It's a statistical model. So you hear all the time about firefighters did not see that kind of fire behavior before. Well, that's because and haven't captured in the models because it's different conditions that were used to develop those equations. Plumes. So what's used for plume models generally now are based upon the chimneys of coal-fired power plants, which it's a lot more complicated than that. There's whole weather systems, micro-weather characteristics that help drive the fire. And fire creates its own weather if you have a big enough system going. The smoke that's generated, it's not all smoke is the same. And what happens to it as it goes up and is transported. And actually, what is the transport mechanisms and how does it change as it's aloft for weeks? You're getting smoke down here from Alberta. A couple years ago, was it this Siberian fires? There was fires from Indonesia and Siberia that were transported across the ocean and was coming down in the United States and have an effect on air quality. So these models in and of themselves have not been adequately validated and calibrated to all the conditions that are out there, which varies tremendously across the country. they have not been well coupled together either. And so this fire and smoke model evaluation experiment is doing these series of highly instrumented fires to better validate these models, to improve them, and drive more to physics-based physics-based model with three-dimensional fuels characteristics. And it's exciting to see that. It's also incredibly expensive to do. But those are some of the partners that are working on that. And this is my revised story map. So we've been trying to figure out at USGS, what's the future science of USGS? How do you integrate and work across disciplines in a way to be able to deal with the complicated interacting factors that are taking place? And so it was polished a little bit, but this was a morning brainstorm of Mark Miller, a friend and my deputy, where we, on the left, kind of mapped out what are the kinds of data and models that are available now that characterize then the blue boxes, which are the main drivers. We have social, political, environmental, and then operational. So social, political are what are the attitudes of people, how motivated are they to do fuels treatment around their homes, defendable space, and what's their opinion of smoke or tolerance of smoke from prescribed fire, for instance. Environmental, you've seen a number of those, but it's the vegetation, the topography, weather characteristics, all those things that could affect it. And operational are fuel treatments, how you respond to fires, the people-oriented stuff, grazing and agriculture, logging, roads. What are the things that operationally affect what you can do? This all then goes to a key hazard or factor like wildland fire. You can do it for any number of other things. In wildland fire, we can describe it in terms of fire intensity, fire severity, fire size, fire likelihood, which is the potential for it to start and spread. And then that affects values, such as wildlife habitat, water quality, lives and property, economic factors, and it goes on, whatever's important to you. So this is sort of a simplified risk model for fire, and then you can cascade this because fire is affecting debris flow, which is a hazard onto itself, or flooding, which is its own hazard. Fire changes the potential for landslides and floods, as well as, again, interacts with invasive species, water quality, and all those. And all these things are affecting back all through the chain and stuff. So trying to understand a conceptual model, how does this fit together? How do we do this? We've done a lot of these different things. Well, there's very few or there's no place that we have tried the whole picture. So let's take the battery of scientists we have available and let's look at it holistically in an area. And so that's what we're trying to figure out how to do. How do we make this more efficient to deal with the complex interacting factors that are actually taking place to change this picture? So I think this is the last slide I have, where to go for more information. So you have handouts. I have